This is part 5 of the series Right Triangles and Trigonometry, and in this part we're going to start with a couple of examples of the right triangle similarity theorem. In this example we have a right triangle and an altitude AD from the right angle. We're looking for the length of that altitude. Now clearly you can see that there's not enough information here to use Pythagorean theorem either on triangle ADB or on triangle ADC. We have nothing about this side or this, but we just know this entire hypotenuse of the big triangle. So we're going to be forced to use the right triangle similarity theorem. The best way to do these is to set up a similarity statement with these three triangles. And that similarity statement is going to guide us throughout the rest of the problem. So let's start out by doing that. Now the way I like to do this is I like to work from each right angle, because those are the easiest to identify angles, these angles and this. And I like to work from the big triangle to the middle to the small. So that's what I'm going to do when I set up my similarity statement. So the first thing, it's triangle A, B, C. In this case I just went clockwise. So we have triangle A, B, C is similar to triangle. Now I'm going to go to the middle one. And I'm going to start at the right angle because that corresponds to angle A, which is the right angle here. So it's vertex D. And I need to go to the angle that corresponds to this angle, angle B. Well, I know that it can't be this because angle C is shared between this middle triangle and the big triangle. So I'm going to use angle C last. So since C matches with C, angle DAC has to be the vertex for this angle. So I'm going to go from D to A and then to C, which is similar to triangle. Now I'm going to go to the small one. Again, I start at the right angle, which is D, and I need the angle that corresponds to angle B. And in the small triangle, B is shared with the big triangle, so it's DB, and then the last vertex would be A. So we have ABC is similar to DAC, which is similar to DBA. Now we can set up a proportion using this as our guide. The next step in this process then is to pick two triangles that I have the most information about so that I can solve for my target side. Now I know everything about the big triangle, and I can use the small one or the middle one. It doesn't really matter because I know two sides of the small one, the x and 3 or x and 4. So it really doesn't make any difference which one I pick, so I'm going to pick the small one. And just so that we don't get messed up, I'm going to underline the two triangles that I'm using so that I can keep this straight. I'm going to start with x, and I'm going to start with the small triangle. So x is 2. X is DA in the little triangle, which is the first and third vertices. That corresponds to AC. AC is 4. Now I go back to the little triangle, and the only other side I know about is BA. So I'm going to use that for 3. And then BA in the small triangle is the second and third vertices, which corresponds to BC in the big triangle. And BC in the big triangle is 5. Now that I have my proportion, it's just a simple matter of multiplying through and solving for x. So x equals 12 over 5. Now just as a cross-check, we're going to verify that this is in fact the right answer. So we're going to say that this is 12/5 and that's x, and 12/5 comes out to 2.4. So this is 2.4. Now we're going to use this and this with the Pythagorean theorem to find out BD. So we know that 3 squared equals 2.4 squared plus x squared. 3 squared minus 2.4 squared equals x squared. And so the square root of 3 squared minus 2.4 squared equals x, which is this side. That's what we're looking for, is BD here. That's this. So let's pull up our calculator, and we're going to do the square root of 3 squared minus 2.4 squared, which gives us 1.8. So BD is 1.8. And if we take that away from 5, then we get 3.2. Now let's determine if this, this, and this make a right triangle. So 3.2 squared plus 2.4 squared should equal 4 squared. So let's pull up our calculator again. And 3.2 squared plus 2.4 squared is 16. And yes, in fact, 16 and 4 squared is 16, so this matches. So this was the right answer. X is 2.4, because this came out to 16 and 16. All right, let's work another example. In this example, we have triangle PRS, and QS is our altitude. We're looking for QS. So just as in the last problem, we're going to set up a similarity statement, and I'm going to start with the big triangle. So I'm going to say triangle SPR. SPR is similar to triangle. I'm going to go to the middle one, and I have to have the right angle, so that's Q. I have to have the second vertex that corresponds to P, and it happens to be P because it's shared with the middle triangle and the big triangle, so that's QP. And then the last vertex is S for the middle triangle, which is similar to triangle. Again, I'm going back to Q because that's the right angle for the small triangle. And I need the angle that corresponds to P. It can't be R because R is shared by the big triangle. So this, it can't be this angle. It's got to be this one. So it's QSR. And there's my similarity statement. Now I need two triangles. And again, we know everything about the big one. So we're going to go ahead and use the big one. And this time, let's go ahead and use the middle one, because we know this side and that side. And so let's see how this works. We have X. X is QS. And QS in the middle one is the first and third vertices, which corresponds to SR in the big one. SR is 5 in the big one. Go back to the middle triangle, and that the only side we know is 12, so we'll put 12 down. And 12 is PS in the middle triangle, which corresponds to PR in the big triangle, and that's 13. Now we multiply through. X equals 5 times 12, which is 60, divided by 13. Now that's a very ugly decimal, so we're just going to leave it like that. And let's go ahead and verify and find PQ. So we know that 60 13ths squared plus PQ squared equals 12 squared. So let's subtract out PQ squared equals 12 squared minus 60 13ths squared, and we'll take the square root of both sides, and therefore PQ equals this. So let's go ahead and put that in our calculator. And we have the square root of 144, that's 12 squared, minus 60 divided by 13 squared. Close the parenthesis, and we get that value. PQ is 11 point, really nasty, ugly number. So we're going to go ahead and store that value. So store alpha A. So we're going to just say, just for the sake of discussion, it's 11.1, and we're going to say we put that in A. Alright, so that's PQ, so it's approximately 11.1. And then we're going to subtract that from 13. 13 minus that value gives us another really ugly number, and that's QR. So we're going to store that in B. So let's make that 1.9. So we'll say that's 1.9, and we're going to store that in B. And now let's see if the value comes out to the same as 60/13. Or we can just use this value and that value, but I'd rather just use these two. So we have this side, which is stored in B, so B squared plus x squared equals 5 squared. Let's subtract B squared, so x squared equals 25, which is 5 squared, minus B squared. Take the square root of both sides. X equals, let's bring up our calculator, and we have 25 minus B squared. This gives us 4.61. And if we look at 60 divided by 13, it's the same value. So it works. So we get approximately 4.61. So our value for x is 60/13. That wraps up this part. In the next session, we'll start a new topic.